Welcome back everyone to this lecture on simple linear regression. We now understand through our series of algorithm theory lectures what's happening under the hood, so to speak, for the actual mathematics behind linear regression. And we're going to start by coding through an example of simple linear regression. Recall that simple linear regression is limited to just one feature. To help with our understanding of this, we're actually going to start by directly using the advertising dataset mentioned in Chapter 3 of ISLR. So if you haven't gone ahead and done any reading in ISLR, I'd highly recommend that you at least check out Chapter 3, specifically Section 3.1. That way you can directly see the mathematical notation that we're going to be coding through right now on the exact same dataset. What's also nice is that this lecture is going to serve to start motivating us to think about performance evaluation and multivariate regression. At the end of this lecture, we're going to have a lot of questions on how we can improve linear regression, how we can take in more features, and how we actually evaluate performance, which will lead us to eventually move over to scikit-learn. Right now, with simple linear regression, as far as coding is concerned, we're going to show that we can actually do this with a NumPy function called polyfit, which uses ordinary least squares. So again, we're dealing with simple linear regression. We're limited to one x feature, so we're just solving the equation y equals mx plus b, which means we're going to create a best fit line to map out a linear relationship between total advertising spend and resulting sales. Let's head over to the notebook and get started. All right, here I am at the notebook. I've gone ahead and imported NumPy, Pandas, matplotlib.pyplot, as well as Seaborn. Let's read in the data set we're going to be using. And this data set is located under the linear regression models folder. And I can say df is equal to pd read CSV. And we're going to say this is advertising.csv. And this is the exact same data set used in chapter 3 of ISLR. So definitely encourage you to read that. And if we check out the head of this data frame, what this data essentially represents is how much advertising in thousands of dollars is being spent on TV, radio, and newspaper for some instance in time, like let's say every week, and then the corresponding sales that resulted. So essentially we want to find out, is there a relationship between how much we're spending on advertising versus the result we get in sales? Obviously, if there is no correlation there, we probably don't want to spend any money on advertising. But in order to do this, we have to actually explore this mathematically. So what is one way we could figure out if there's a relationship between advertising spend and sales, especially if we're limited to just simple linear regression of just one feature? Right now, we technically have three features: TV spend, radio spend, and newspaper spend. But if we're dealing with simple linear regression, we're limited to just a single feature X. What we could do is just combine all of these into total spend. So I could say I have a column, total spend, and set it equal to the sum of my expenditure on TV, radio, and newspaper advertising. So I could say df TV plus df radio plus df newspaper. And now if I take a look at my data frame, I'm going to have what is essentially an engineered feature. This is total spend, and the reason it's engineered is because it didn't exist, technically speaking, in the original data. Instead, I used original data to create a new feature. Now, this isn't a very particularly insightful feature. In fact, it's just aggregating data itself. Later on, we're going to explore feature engineering for the use cases of actually trying to extract more information, not just aggregate information. But what is nice about this is now I have a y vector, sales, and a single x, total spend. Let's go ahead and visually explore if there appears to be a relationship between total advertising spend and sales. One way I could do this is with a simple scatter plot. I could say sns.scatterplot, state that my data is my data frame, and then I'm going to say x is total advertising spend, and then y is the corresponding sales. And if I run this, I get something that looks actually pretty intuitive. I can see that the more I spend on advertising, the likelihood is that I'm going to get more sales. There's clearly a positive regression fit here where I can see that I'm getting more sales for more advertising spend. So there does appear to be a relationship between total advertising spend and sales. And what's interesting is that if you take a look at the Seaborn library, something we haven't shown you yet is that there actually exists a reg plot, which is a regression line plot. For the case of simple linear regression, where you just have one y vector and one x feature, Seaborn is actually able to plot out a regression line using ordinary least squares. And then if you run this, it will show you the line of best fit on top of that scatter plot. So then the question becomes, how can we actually calculate what this line is? This is a simple y equals mx plus b line. How can we actually use this? Also, what's important to understand is if I have this best fit line, I could try to predict the expected sales for any total spend value. I could say that if I intend to have a total advertising spend of about $400,000, I could come back up here, take a look at where my best fit line is, and say I would expect some sales kind of around maybe $22,000. Okay, so then maybe a question arises, if our next ad campaign is going to have a total expenditure of $200 or $200,000, how many units can we expect to sell? How many hundreds or thousands of dollars can we expect to sell? So for some x, what is going to be the expected y? Well, what we can do is just separate this out and say x is equal to df, total spend, and y is equal to df, sales. And I'm just using capital X here to line this up with the notation we're going to see in the future. Technically, this could be a lowercase x since we're just dealing with one feature. But this is the convention we're going to be using throughout the rest of the course. So I will just go ahead and start it now of having a capital X for our feature matrix and a lowercase y for our expected label or target output. Now that I have my x and y defined, I can solve that ordinary least squares equation. And previously, in our algorithm theory lectures, we actually solved OLS by hand. However, we have so many points here that it makes sense to let the computer solve ordinary least squares for us. And NumPy actually comes with a function that does this for us, and it's called np.polyfit. And if we call help on it, we can read the documentation, and we see it does a least squares polynomial fit. And the reason it does a polynomial fit is because you actually have the option of not just fitting to x, but also fitting to x squared or x cubed in addition to x. In our case, we're just going to say degree of the polynomial is equal to 1. Because recall, all I want to do right now is create an equation, y equals mx plus b, for the best fitting line for this real set of data points. And if in terms of beta coefficients, that's just going to look like this. It's going to be beta 1 times x plus beta naught. And what polyfit returns for us, if we provide the y and x values, are the set of coefficients solved by ordinary least squares. And since we're going to say degree is equal to 1, it's only going to consider x, not something like x and x squared or x cubed. So let's go ahead and check this out. We'll say np polyfit, and it requires your real x and y data points, and then the degree we want to fit this to. We'll say just degree is equal to 1, so just fit it to x, not x squared. And when we run this, we get back two numbers. And these two numbers are these actual beta coefficients. So it just returned 0.048 as beta 1 and 4.24 as beta naught. Now, what can I do with these coefficient values? I now have coefficient values that for any x, it will predict the y. So for any total spend in advertising, it can predict the sales. It's essentially the equation of this line. So if we want to actually plot out this line, I can create a series of points from, let's say, 0 to 500 for total spend, and then predict the y values to get a bunch of points to fit this line. So what we're going to do here is say my potential spend is equal to np.linspace, and let's go from 0 to 500 and give me 100 points between 0 and 500. This is just some theoretical potential spend in advertising. Now what I'm going to do is calculate my predicted sales for each of these potential spend values. Again, they're just all values from 0 to 500. And the reason we chose 0 to 500 is because more or less that's the range of our data set. So we're going to say predicted sales, and now I'm just going to calculate this equation right here, beta 1 times x plus beta naught. So I'll say my beta 1 is this value right here, and it returns them in order of highest order coefficient to least. And then we're going to say that beta 1 times our potential spend plus beta naught, which is this value right here. So copy and paste that there, run that, and now I have some made up potential spend values, 100 values from 0 to 500 evenly spaced, and then the predicted sales for all of those theoretical expenditure values. So I can actually plot this out, PLT plot, the potential spend versus the predicted sales. And now I get this regression line. And let's explore visually how this regression line fits on top of the data. So right before we plot this, I'm going to say SNS scatter plot and repeat the scatter plot from above, where we have total spend on the x-axis and then y is equal to sales on the y-axis, and my data is equal to df. And let's go ahead and color this line. We're going to say this color is red just to make it very clear. You run that, and now I have the line that I just fit, that equation y equals mx plus b, on top of the real data points. And that is pretty much the exact same thing that Seaborn just did right here. Obviously, the scale of the y-axis and x-axis is slightly different if you just call SNS regression plot, but that line is the exact same thing we're showing here with our own manual calculation using np.polyfit. And now, with this equation of y equals mx plus b, I can essentially answer the question if our next advertising campaign is going to have a total expenditure of X amount of dollars, how many units do I expect to sell? So what I can say is say something like, I'm going to have an expected spend of $200. What is my predicted sales for that particular advertising expenditure? I could say predicted sales is then equal to, and we're pretty much just going to plug in 200 to this equation that we have here. So I'm going to copy and paste this right here. And then instead of potential spend, let's just pass in spend, the $200. We run this. And now I check out my predicted sales. And I have 13.98. Does that make sense? Well, if we take a look at the line, pretty much. If I have a total spend of 200, I would expect to have total sales value of around 13.98, so around 14. All right, we've pretty much completed what we set out to do. We were able to solve ordinary least squares with Python using np.polyfit to figure out some equation y equals mx plus b. Now what I want to do is just quickly explore further considerations that we're going to discover in future lectures. One is just actually measuring performance. Right now, we have just a straight line here, but how good is this actual prediction value? Notice I predicted sales of 13.98 with a corresponding spend of 200. How do I actually determine whether or not that is a good value for prediction of sales? So clearly, we have to eventually do a train test split as we discussed in the machine learning overview section. And just running polyfit like this with ordinary least squares is not the best way to do that. In fact, we'll see that scikit-learn has a lot of built-in tools to help us out with that train test split. So right now, we're severely lacking in actually measuring performance and understanding if we're overfitting or underfitting. And we'll discuss in more detail what overfitting versus underfitting actually looks like. We also discovered that polyfit could technically take in higher degree polynomials. We just fit y equals mx plus b, but we could be fitting to some second or third order equation. Let's take a quick look at what that looks like, and then later on we'll discover how we can perform polynomial regression with scikit-learn. But in theory, I could do it for just a single x by calculating the fit for x cubed, x squared, and x all together. So the best way to do this is just kind of play around with it. We're going to say np.polyfit. I'm going to pass in x and y again, but this time let's do a third polynomial degree. So when you run this, notice you're actually going to get back 4 values. This is for x cubed, this is for x squared, this is for x, and then this is for just the y-intercept, which means instead of solving the equation y is equal to beta 1 times x plus beta naught, we actually just solved the equation y is equal to some beta 3 times x cubed plus some beta 2 times x squared plus the beta 1 times x. Notice it's going to be a different beta 1 value than this one because now we're taking into consideration the cube and the squared. And then we have also some new beta naught value. So these are the beta values that correspond with this polynomial fit. So it's fitting to a higher order. And keep in mind, if there's actually less information on something like x cubed or x squared, essentially saying that there's no real higher order relationship there, then these beta coefficient values are going to get quite small. You'll notice that the relationship for x cubed versus y is almost non-existent. The way we know this is that the beta coefficient here is 3.07 times 10 to the power of negative 7. This is actually almost zero or very close to it, which essentially says go ahead and don't even consider x cubed because it's not really a factor here. So what does this look like if we actually plot it out? We can do the same thing as before, create some sales values or spend values. So I'm going to say pot spend for potential spend is equal to NP linspace, and again we'll say 0 to 500, give me 100 points. So I'm going to have all these potential spend values, and now let's have predicted sales, but using this polynomial equation instead. So I'm going to say my pred sales are equal to, and this is where we're going to grab all these coefficient values and start putting them in. So here is my beta 3, which means I need to multiply that by potential spend to the power of 3. Next, I need to grab this coefficient, beta 2. I'm going to put it in there. And then I'm going to say I need to multiply that by potential spend to the power of 2. Let's do one more. Here, this beta coefficient. This one's going to be the beta coefficient times just potential spend, so essentially just x. And then finally we have our y-intercept, which is going to add on this beta naught value. So we can copy and paste that here. And I'm going to zoom out just a little bit so we can see the whole equation. So again, all I'm doing here is I'm manually writing out this equation. Y is beta 3 times x cubed plus beta 2 times x squared plus beta 1 times x plus beta naught for these values of potential expenditure. So then I'm going to have this array of predicted sales for all these potential expenditure values when I'm considering not just x, but also the relationship between x squared and x cubed. So when you actually run this and then plot it out, we can say, in fact, the same thing as before. Let's go ahead and copy this code, paste it in here, and then let's, instead of potential spend, say pot spend and pred sales. Run this, and you notice as you increase the order of that polynomial, you start to get these curves. Now, how do I actually compare these values? Is this a better fit than this linear fit? Well, so far, we haven't really discussed a way to evaluate performance metrics for regression problems. So clearly, we have some motivation here to try to understand how well our model is actually performing. I right now have two models, and just visually, I can't really tell if a linear fit is better than this curved fit, which means I should start calculating quantitatively what my error is and what the better fit is. So we're going to explore all of that in future lectures. But hopefully this now gets you thinking about different models and comparing performances between different models. We have a high-level polynomial model and just a simple linear fit model, and we want to be able to compare them. Comparing models is something we'll see a lot when we discuss machine learning. And then finally, the last consideration I want to point out is we've been doing all of this with just one x value of total spend. But it'd be nice if I could actually evaluate all of these independently of each other, understand the relationship between just TV and sales versus total expenditure and sales. Maybe TV ads do a lot better than newspaper or radio ads. So clearly we have a need for more features, and for that we'll need linear regression as well as gradient descent, as we discovered in the algorithm theory lectures. Okay, so lots of potential for improvement here. We'll discuss everything that's going to happen with scikit-learn in the next lecture. I'll see you there.